Hi everybody, Evan again, back with another video about the dew point and bubble point for a binary chemical mixture. If you remember last video, we talked about what is a bubble point and a dew point, how to derive it from the Raoult's law, and then applying the derivation into Python to get a calculation for bubble point and dew point at a constant temperature and a constant pressure, which is basically what you see here on part A. Today, we will be using the derivation that we used in part A and actually using using the vectors and putting those vectors onto a graph to see the actual curves for the bubble point and dew points. So in part B, what we're doing for part one, we will be assuming benzene and toluene have a ideal behavior, so equilibrium, how to co-generate the plots to do for dew and bubble curves for a constant temperature and a constant pressure. Second, we will be plotting a y1, x1 graph at a constant pressure. And then three, we will derive an expression for an y1, x1 graph, assuming constant relative volatility. And then using the fixed relative volatility, calculate a vapor pressure at 373.15 Kelvin, and then compare results to what you obtained for part two. So let's get started coding. Okay, so fresh one. First, like always, we'll be using this website at GitHub and using the library in GitHub import MB for our chemicals for today's code video. So if you want to follow along, feel free to copy this link, pause the video, copy this link, and then you can import it into your code. So for me, enter. All right, and then the libraries we'll be using today is, of course, import MB. So from import MB, import notebook, and then with notebook, and from CHE5, import props. Okay. All right, which is where we get our benzene and toluene. We'll also be using NumPy for our arrays. So from NumPy, we import NumPy as NP, and then we also be using SciPy for our root solver. So SciPy oh, from SciPy.optimize import root. All right, hit enter. Okay, make sure everything's good. All right, good. So then first let's pull our chemicals. So use P, so P props, parentheses, brackets, benzene, and then comma toluene. All right, should enter. And then for this, we'll also need the composition. So like we said, the liquids are like ideally so if assume they're equal molar. So we're gonna do Z for today. Z is equal to MP dot array. And then parentheses, brackets, 0.5, comma 0.5. Okay. Oh, hi. Let me put a 0 there. So, all right, just right. Okay, first, we will need to generate the code for the dew point and bubble point curves. So I'll do bubble point first, like we did, started off yesterday, our last video, and we can start out with a constant temperature. So we'll be finding the bubble pressure. So define bubble P ideal. And then molar composition at a constant temperature. And then today we'll be doing it a little bit more simpler. I had to clean up, but we clean up, make it easier to read. So we're gonna be finding our P, our pressure, which is equal to, so we need NP is the sum, click the sum of our formula that we'll be making, and then molar concentration, liquid molar concentration times the vapor pressure, P vap, our respective T. Okay. And all this basically is, if you remember, a Roche's law, liquid composition times our vapor pressure is equal to our vapor composition times our pressure. Okay. We want vapor pressure by itself, divide both sides by P. P, this, and if you also remember Y, two compositions of Y will be equal to 1. Okay, so we substitute that. The 1 for Y gives us this, and then now we want to solve our pressure. To solve our pressure, we will multiply both sides by P, and this will be, so this is basically what the formula is saying right here. I won't forget dot P dot P back. Okay, this is what it's saying right here. Yeah, pressure is equal to liquid composition times vapor pressure. Okay, so put that there. All right, and then we need to return RP. I should enter, then bubble P deal at composition, and we know the temperature would be at 373.15 Kelvin. So should enter, and bada bing, bada boom, it shoots us out the pressure at the 373.15 Kelvin. Okay, but today we will also be needing the molar composition as well at the respective temperature. This is due to the fact when you plot something, you need more than one known vector. You need two to combine them to make a XY plot. So we may have our X, we need a Y. So we need our composition to also as well to introduce in our plot. So for this is just Y is equal to uh, X times P vap, straight to T, and divided by B. That's all this is. So we're just using this formula, we get rid of the Y is equal to, and this would be calculating the molar composition at the respective temperature. So, okay, so should enter, should enter. And you can see here, it will tell you now the composition at the respective temperature. Okay. So now let's do the bubble, temperature. Okay. I respect that at a constant pressure. So if F definition bubble T ideal, and then composition, more composition, and then pressure this time. And then also same thing like last time. They need the pressure differential of the bubble pressure and then the pressure of the system. Okay, so P def, write the T, turn, bubble, and then it should be water composition times D minus P. But here we need to also add bracket 0. So this is basically saying that when we pull this and we push shift enter, we are pulling the value, the array here. Okay. If we just let this out, remember our answer is not with a molar composition. So this was basically saying it'll be pulling this pressure and also the molar composition as well. And the code get confused, it doesn't know, it has too many numbers to generate and it won't give you an actual number. It'll give you an error. So I will show you here. Deal. All right, let me show you. Return. Let me say T is also equal to, so temperature, square root, and let me say 300. Okay. And return T. And then bubble T ideal at Z. And then we know it's 101.325. Shoot you out error. Let's support operating types of tuple and integers. Okay. So this is because this is a tuple. We have an integer here. We need to just get this integer. Okay, get the pressure. So let's single this out. Bracket 0. Okay. 0. Okay. And then I guess I'll do the same thing here. Dot X bracket 0. All right. And we also want the molar composition as well. So let's same thing as the bubble pressure. Liquid composition times PVAP divided by Y. Divided by P. Okay. In respect to T. All right. No P flow. Let me just run it all again. What is the problem? Right back. Okay, so final problem. We just finally got to put the comma here. So then shift enter, it will work again. So that's all good. And now you see again the temperature 365 kelvins. And then you'll see the arrays here as well. Okay. Oh, get this out of here. All right. And then see the arrays here and all the concentration. Okay, so now let's do the dew points. Okay, so def dew underscore, and we start at constant pressure again. I mean constant temperature. So finding the pressure. Dew. So use the vapor composition, and then constant temperature. All right. Then we say P is equal to 1 divided by NP sum of Y times P dot PVAP respect to T. Oh no, divided by P dot PVAP. This again goes back to our Luke's equation, x is equal to y times P divided by PVAP. Okay. Remember, this is also equal to 1, so we replace this with 1. Then we also want P by itself. So we put P by itself over here. Divide P by both sides, we get 1 over P is equal to 1 over PVAP, and then put it to the first power. So we flip it over. So you put P here. P is equal to 1 divided by liquid vapor composition divided by pressure, vapor pressure. Okay. You can also just do PVAP divided by Y, you should say answer. Okay, so here's a formula here for this. Okay, we'll return P, and then this time our molar composition will be Y times pressure divided by PVAP. P dot PVAP. Okay. Shift enter and do P underscore ideal molar composition, and then again temperature is 373.5. Okay, shift enter. It's supported. What does that mean? You just run it all again. Oh, forgot to put the respective temperature on here. That's why shift enter, bam. Got our pressure at 104.894 pascals, and then our compositions here for benzene toluene. And let's do dew points expected pressure. Let's see. Ideal, molar composition, pressure. Okay. Also do the pressure differential. So def P dev back to T. Okay. Return do do differential pressure. I mean the pressure, the dew point pressure. Ideal, and then liquid. I mean vapor composition, and then expect the temperature. Be pulling out the first array, and then again minus P because it's just the pressure differential between the dew point pressure and then the pressure system. Okay. And then we're finding temperature. So P is equal to root of P dev. Scale it to 300. And we want we want to pull out the temperature. So dot X of the pressure. Okay. And then we return temperature and then also the molar composition at that pressure divided by P vap. Okay, shift enter. And then do T ideal. And then 101.325, shift enter. And here. So this is the code, the entire code that we'll be using to plot out our XY plots for dew points and bubble points. Okay. Pretty simple, kind of like the last video, just a little bit of difference. Okay. So now let's get to the second part into plotting our graph at a constant pressure. Okay. Well, first, before we do this, we need to first figure out how many points in our graph we need. Okay. So when we need the concentrations, that'll be our X. Okay. That'll be, any point sections we'll need in our graph. So we'll call this Z1 is equal to NP line pace. Okay. Okay. 0. So basically all this is, it is taking the section of numbers. So I'll just put the whole thing up and then I'll explain it. So 0, 1, and we can do 10. Okay. So this all this is taking the numbers 0 to 1 and all the numbers in between it and it's separating out evenly into 10 gaps. So we have 10 numbers from through 0 to 1 that we'll be plotting on our graph. So shift enter. It's not 9. Okay, guys. Okay. Let me if we plot out Z1. You see, so 0, 0, 0, exactly. We can do 100, we can do 6, gives us 6. Okay, we can do 20, gives us 20. Okay. But it gives us 20 numbers in between 0 to 1 that we can use for our graphs. Okay. And next we will also we need to put our two concentrations for benzene and toluene into 2 columns. Okay. So this what we can call this Z's is equal to NP dot C pound, and we'll be using Z1 in comma 1 minus Z1. Okay, so that C class is not callable. C class is not capable. Shift enter. Okay, So the problem here is that I actually put these in parentheses where they need to be brackets. Okay, this is the one weird thing about the NP.C, which columns, is that it puts this into, you need brackets to the columns. So, like I said before, this is basically putting all of our numbers that we were using into columns for our graph. Okay, so we put this here, use Z's, shift enter, shift enter. It uses all the plots from our NP line space, all the numbers in between 0 to 1, and it puts it into a column, okay, that we can use for our X and Y axis for our plots, okay? All right, so let's get started. So for our plots, we know that we need a plot that is constant P at 101, 325. Okay, so when we need an x-axis, so we have our x1, we do x1. Okay, we calculate x1. Okay, so x1s, so all of our x1s. And again, this is in brackets, columns. Okay, our y1s. Okay, so on our y-axis are the y concentrations. And then all of our t values. So in our quantity, we'll be using the t's. We'll be needing to find all the t's corresponding to all the concentrations that we're using in our given point, in our given 0 to 1 points. Okay, so all of our t t values. Okay, we know pressure is equal to pressure is equal to 101,325 pascals. Okay, all right. So then now we would need to state this column. Okay, so for Z and Z's. Okay. You will be needing to find, so let me start this over. So for our plot, we will need first to define our y-axis, and then our slope basically. So for our axis, for our x-axis, we need the x1s, okay? All the values for our x-axis, all the values for our y1s, our y-axis, so the y1s. So doing this from the benzene concentration. So the concentrations of benzene, so the concentrations are all the benzenes, vapor concentrations of the vaporenes, ratios, and then the RT. So again, the prompt is saying for part 2 that we need to plot out a graph at a constant pressure, 101,325. Okay, so we are using we'll do the bubble point for this one, but we're using the bubble temperature for this graph. Okay, so for our P's, for our T's, all the values for our T's. Okay, and remember these are all in columns, just like this. We need all of our sections to be columns for our graph. Okay, we know the P is equal to 101,325 pascals. Okay, so let's plot this out. Let's put the code to define all these x1s, y1s, and ts. Okay, so for Z, this is our molar concentration, and Z's is our column that we stated. Okay, T, temperature, and Y equal to our bubble, T, ideal, and respect the molar concentration, respect the pressure. Okay. Now, okay, running out of time. We'll get this done fast. All right. So we have our Y's. Oh, we need to pull our ones, or Y1. So Y1 X1, we do our X1s first. X1 dot append. So this will be for the X1s, we'll be using the molar concentration. So Z, and we'll be pulling the first one, the benzene. So we need to specify it as 0. Okay. Enter, and then the Y1s dot append. We're doing the Y, so the Y, and then 0. So the first of the benzene for the Y for the vapor. And then for our T's, temperatures, append. This should be our temperature to be fine. Okay, so these are the definitions for X1 5 P1. So for Z's, with respect to the temperature and the vapor and the bubble temperature ideal, we're using our X1s, which would be our molar concentration of benzene, our Y1s, which would be our vapor concentration in the benzene, and then our temperatures, the values, which would be expected to. Okay, so now let's plot this. Okay, so now that we have our code written down, generated, now let's plot out our vectors for our dew points and bubble points. Okay, before we do this, we need to import a library that you can plot anything on Python, and we'll be using plotly.subplots, and then import make subplots. So now this allows us to now generate plots in our code. Before, as we weren't able to do this. So now we are able to finally make these plots to use the vectors and arrays that we made and pound down on a plot. So now let's make this plot for this, for the bubble point, bubble T, respect, and a constant B. Okay. First, we need to start with we call this, we just keep it fig is equal to make subplots. Okay. Parentheses. This just generates the plot that we want to make. So it generates the graph. Okay. So then when we want to add our vectors to this graph, so let's add our first vector, will be the the bubble curve. So fig dot add scatter. For our x-axis, we'll be representing this with our x1s, our liquid concentrations. Then our y will be respect of the T, the temperatures that we're collecting. And the name for this, we will just put down bubble for our bubble curve. Okay. We also need to add one for our dew point curve. So fig dot add scatter, and then x is equal to our y1s, and then y is equal to our TS temperatures, and then name equal to okay. Y1s are not defined. Why does it say that? Y1s. Oh, I did L, my bad. Okay, and then lastly, we need to have the dimensions of our plot. So the height, width, where our title will be, the legends, stuff like that, the color. So we would put in fig, the updates, and then the layouts. Like spell it. And then we start with our width. So width, we'll put in the scale of 600. Our height, also do scale of 600. Next, we would do our template, which is the background of our template look like. We can do one a dark view, so it doesn't blind us how bright the plot is. So we'll do plotly dark. Okay, and then for the title, we want our title to be benzene first mixture versus toluene second. And if you want to plot out what pressure are we using, we'll do P is equal to curly brackets pressure. And for this, we need to add F to F. You see here, it highlighted, it made the variable P, which we'll be pulling from here, visible and not just as a comment, as a string. Okay, now this is an integer. All right, now if we Control Shift Enter this should plot out our desired plot. So Shift Enter, and bam, here we go. As you can see here, it shows our, in the red, it shows our dew point, and on the blue, it shows our bubble point. The y-axis is our temperature, and the x-axis is the concentration. All right, but that's also not what it asks for. That's what it asks for part one. With part two, we are asked to just plot out the y and x1's concentrations in respect to the constant p. So let's plot that out as well. So for this, we'll be just using the x1s, y1s that were used here, and we would just use also the constant p as well. So here we can also just say fig is equal to make subplots. Okay. Parentheses, we want to add our first line, which would be our concentrations of the ratio of the liquid composition and the vapor composition as the temperature rises and falls. Okay. So here we're gonna fig dot add scatter of x equal to x1s and y is equal to y1s for both our concentrations. We can leave it like that. Fig dot add our next plot, which this one we would just have a XY plot, XY line. So y is equal to X line on the graph to compare how the bend of our concentration will be compared to a regular diagonal line. So we're here for our X. We'll put in bracket 0 to 1. So from nothing in our concentration to 1 in our concentration. And then we do the same thing for the Y. Come on, 1. Oh, let me write it. 1. Okay. 1. And here we specify that this would be a line. Okay. And also when this pops out, this would be a bright red color. So if you want to make it more neutral, we can just put in line color, pound color to equal to, I do Orby bib, red, green, blue. And then have a mixture of 50% red, 50% green, 50% green, and 50 blue. Okay. Now the layout of our graph, so fig update layout, and then we can make it smaller. We just do 500 this time. So 500 height, same thing, 500 template. We can say same thing, probably dark. Dark. All right. We don't need a title. If we do want to, we can say title is equal to molar ratio comparison, molar ratio comparison to x1 versus x2. All right, and then should enter. And here's our plot. So the blue line represents the concentration we see over the span of the temperature changing. Okay, and then the black one is just in the straight line, diagonal line of y is equal to x. So you can see the difference in concentration change as the temperature increases or decreases. Okay. that's part two of what we've been asked to do. So now part three, derive an expression for y1, x1, assuming constant relative volatility. Using a fixed relative volatility, calculate the vapor pressure at 373.15 Kelvin. Compare results with the obtained in part B, in part two. Okay. So before we get into it, let's just assess a little bit about what is relative volatility. So relative volatility is just a comparison of vapor pressure in a liquid mixture. So for that represents is P1 divided by P2. So is the vapor pressure of our species one divided by vapor pressure of species two. And this is represented by the term alpha. Okay. So alpha is equal to the vapor pressure of species one divided by the vapor pressure of species two. Okay. And how this will look like if we put comments in here. Our graph is for, we can do x1. So x1 first, it'll go out as x1 times p-vap, p1 vap. We call this, we can just say p1 is equal to y1 times p. So our liquid concentration times the vapor pressure. Species one is equal to our vapor concentration times our pressure. Okay, and then we know the second equation for x2, y2 is x2 times P2 is equal to Y2, Y2 times P. We know this also equals out to 1 minus X1 times P, okay? And is equal to 1 minus Y1 times P. And we know this by, remember what we said earlier, that X1 plus X2 is equal to 1. And it's equal to 1. And that's how we were able to solve all our equations earlier, what we stated up here for our concentrations. So that's basically what this equation says. So you can represent the equation like this or like this, but we'll be representing the species two equation like this. Okay. And then if you divide species two over species one, you will get something like this. So you will get x1 divided by comments. X1 divided by x1 and 1 minus x1 times p1 divided by p2, which would be equal to, same thing on the right side, y1 divided by 1 minus y1 times p. Well, times 1 actually. So I'll cancel out p over p. You cancel out the 1, so just 1 over 1. y1 over what? Over y1 over 1 over y1. Okay? So this is the new expression if you divide species one equation divided by species two. Okay. And then for here, we will be trying to compare, since relative volatility is a comparison of vapor pressure, you want to know the vapor composition in this as well. So we want to move out, but we want the y1 by itself. So we multiply both sides by 1 over what? 1 minus y1. So this will give us, put this in double brackets. Okay. Divided by 1 minus y1. Okay. Okay. So actually, that's fine. Okay. So from this, actually, let me pause. Okay. Small mistake. But actually, the y over y1, since it was on the denominator, we multiply on both sides. So we multiplied on both sides. You had to distribute this out between the function on the left from the 1 minus y1. And then from the algebra, we'll get at the end. This will be a lot of work to algebra we can do by hand. But we will get at the end alpha. Remember, P1 divided by P2 is equal to alpha. So alpha, I'm going to state it up here. Oh, I state it up here, actually. Alpha is equal to P1 over P2. All right. So we can change this to alpha. At the end, though, we will get y1 is equal to x1 alpha times alpha divided by 1 minus x1 plus x1 times alpha. Okay, so this is saying that the vapor concentration or relative volatility from the both equations. So the vapor composition and power composition and benzene is equal to the liquid composition times relative volatility divided by 1 minus the liquid vapor composition plus x1, which is plus the liquid composition times alpha. Okay. So this is what relative volatility is basically. So it's this is comparing the vapor composition between both equations. Okay. So now let's plot this out. Okay. So we want to define P1 is capital P1 and P2. We will set this equal to 373.15. Okay. Okay. So to start off, we wanted to find out both of our vapor pressures, our P1s and our P2. So we would say P1, P2 will be equal to P dot PVAP. And we know from our prompt that it needs to be 373.15 degrees Kelvin. So 373.15. Okay. And also, like we said earlier, alpha is equal to P1 divided by P2. Okay, so shift enter. Okay. The next thing you want to do is have our x1s and y1s represented. So for this, we can just take this as x plot. Okay, so we used x1s earlier. We just might as well just use something different. So we do x plots. Okay. So x plot will be equal to np dot line space 0, 1, and then we do 50. So like we stated earlier, and let me see if I can find it for you guys. And here for Z1s, we're doing the same thing for our X1s. So we want to have multiple evenly spaced out concentrations from 0 to 1 that help us align with the concentrations that we'll be tracking with this plot. So for our X plot, we'll be using NP line space for 50 evenly spaced out lines. Then for our Y plots, should be equal, like we said earlier, x1 times alpha. But in this case, x1 is our x plot, so it'll be x plot times alpha. All right, shift enter. All right, and then from this, we have relatively everything we need. We can start plotting this down actually. So, oh, actually, no, I'm sorry. Y plot is actually a log equation. It's the equation that we find out at the end that the y is equal to x1 times alpha divided by all that. Yes, so this would actually be this equation. So it'll be alpha, x plot times alpha divided by 1 minus alpha, x plot. Okay, we can do double bracket here, plus alpha, x plot times alpha. So here is the characteristic equation for the y plot. And this is basically what we stated earlier. Excuse me, that the y1 is equal to x1 times alpha divided by 1 minus alpha. No, x plot, the x1, sorry. And then plus alpha times x1. So that's really what this represents right here. Okay. Now we have everything we need to plot. So now let's plot our thing. Now let's plot this on our graph. So same thing that we did up here, same kind of configuration. So we'd start with fig. We'll call this fig 3. Since this is our third plot, we'll call this fig 3. So fig 3, so you're gonna make subplots, parentheses, fig. Well, for our first vector, we'll add the, I think how to bring for. We will add the x plot, y plots. So fig 3 dot add scatter. X is equal to x plots. Okay. Y is equal to y plots. Okay. What is it? Oh, I said plots. Y plot. And then mode is line. Okay. Lines. And then next line. You will have our XY diagonal line. So fig 3 dot add scatter of x is equal to 0, 1. Then y is equal to 0, 1 as well. Correct that in here. Okay. Mode will be equal to lines as well. Then the line color will be equal to RGBib. Then 50, 50, 50 like last time. Okay. And lastly, we will make our layout, our plot, our overall layout of our plot. So fig 3 dot update layout and width be equal to 400, do 500 like last time. Kind of represent same things. Get a comparison like we're supposed to do. Height is equal to 500 as well. Okay, and then template is equal to slightly dark. Okay, slightly dark. And then we don't need to show a legend for this. So we can just put in show legend is equal to false. Okay, so this will not pop up a legend like this one does, is be blank. Okay, so this should be all that we need for our plot. Shift enter. Hmm. No property special graph. Show legend. Hmm. Okay. Simple spelling mistake. Okay, now we should begin now. Yep. So here's what our plot looks like now. And let me zoom out. Let me zoom out so you can see both plots. So this is what the plot looks like for relative volatility. And as you compare both of these, you can kind of see that they're basically similar in this thing. Um, there's no real big difference between both of these plots, which is very good. Not good, but you can see there's no real big difference. So which means our vapor pressure and our relative volatility in respect to our vapor pressure respect to this constant P and in respect to relative volatility are ideally the same. So yeah, that's all I have for today. Hope you guys enjoyed the video and until next time, thank you for watching. Bye.